Okay, so today we are going to discuss the first assignment which has been given to you. So, in case of any questions you want to ask for clarification, you can ask, right. So, the assignment has already been posted on the web. I hope you have gone through it. So, I will just go step by step for the various components of the assignment. So, assignment actually has 3 components primarily. The first component deals with the polygon clipping, right, which is 2D polygon clipping. The second component is about filling of the polygon, right. So, one needs to have that these two are linked. So, once you have done the clipping, you should be able to do the filling of that clipped polygon. And the third component is the entire viewing pipeline, so various viewing transformations which we have studied, right. So, let us look at the, let us say, the input output specification for these components. So, the first one is the polygon clipping. So, basically you are required to do the implementation of Sutherland-Hodgman polygon clipping, right, which works for a window, an arbitrary window of which is of convex type, right. So, the window would be convex, whereas the polygon which would be clipped can be convex or non-convex. So, you have to show both the cases, okay. And while you are doing this test of clipping, you need to find out whether the particular polygon which has been given to you is convex or not convex. Therefore, there is a test of convexity which you need to perform. Okay. Let me add maybe some motivation for those who may want to do non-convex windows. Obviously, the standard Sutherland-Hodgman would not work, right. So, those of you who want to try non-convex windows will get some bonus. Okay. So, you may consider that as a bonus to you. Fine. Okay. So, the test of convexity we have seen how to do it, right. So, which is the specification or a requirement for the assignment. So, so what are we expecting from here? Basically, that you have, this is what we have seen earlier, we have some polygon which is non-convex here or convex here, right, and the window is a convex window. So, here we have considered a rectangular window, and this is the result which is obtained. Okay. So, for this part of the assignment, I have filled this polygon, but we are basically dealing with the lines of the polygon, edges of the polygon. Yeah.
So, for like when we are handling all the 4 cases in Sutherland-Hodgman,
Right.
then we have to check whether a point is inside or outside. So, for that we can use ideas similar to what we did for Cyrus bed.
Correct.
So, sir, but in those cases, how do we identify which normal is the inward normal?
So, that is the convention you would give in, right. When you specify the window, I have the notion of these edges, right. These are the input given by the user.
So, the input will be just given as coordinates of the vertices, or which
an order. See, you can specify an order of the specification of the vertices, which would in turn determine which is inside or outside. Isn't it? See, if I give in one order, anti-clockwise or clockwise, that defines what is inside, what is outside. Okay. So, this is the input specification you give and have that as a convention to be able to decide which is inside, which is outside, right. Okay. So, this is the kind of result we are expecting out of the polygon clipping, right. So, the next thing, the next component is the polygon filling. So, again when I say that you are giving the number, the endpoints of the polygon, right. So, basically you are specifying a vertex list and the corresponding polygon, right. And you may actually have a data structure which allows you to have multiple polygons, because when you use the description of a scene later on, then you can use the same data structure. Okay. So, try to build things modular so that you can use them later, right. Okay. So, here what are we saying, that basically we have looked at the algorithm, the way it works. So, there are two algorithms which we have studied, right. The first one was the scan line conversion, right. So, you go scan line by scan line, right, and find out the intersection of that scan line with the edges of the polygon, right, and then look at the spans of those scan lines which are intercepted within the polygon and fill them, right. That was the algorithm. The other algorithm which we studied was basically filling, seed filling, right. So, you supply a seed, find out the neighborhood of that seed and then propagate the filling from that seed, right. So, and you can consider either a pixel of the type having 4 connected neighborhood, or you can also consider 8 neighborhood. Okay. So, here I am not specifying, let us say, which algorithm to use, but let us say I expect at least the scan line conversion. Okay. So, here what we are saying is that you will find out something like the points x l and x r of a span within the polygon, and then you will actually render this line using OpenGL. Okay. So, I am not expecting you to actually find out all the pixels here and then color those pixels. So, here you can use the primitive of OpenGL like a line and just render that. Is it clear? But you have to account for all the possible ways in which you can optimize the computation, right. So, the scan line coherence, for instance, is required. That is what you are doing, finding out these spans from one scan line to another scan line when you move, right. So, interscan coherence, that is also exploit using the edge slopes, right. So, all those things have to be in your implementation, right. Okay. So, and you should be able to handle both convex polygons and non-convex polygons. Okay. So, for instance, you should be able to handle this, and here also the special cases which would be required for you to handle when the scan line passes through the vertex. Okay. So, which is, so this particular thing is done through parity checking. We have done that. So, you know what the algorithm is. Fine. So, things will be little interesting when you are doing seed based method. Those of you who also opt to do the seed based, then they can compare it computationally, right. So, what do you expect? Which is going to be faster? This one is going to be faster. Okay, well, find that out. Okay, so next you also need to basically connect these, right. So, what are we doing as clipping? That is the input given for filling. Okay. So, that way, for instance, if you perform a clipping on this is the clipped polygon, then you should be able to apply your filling algorithm on this. Okay. Next, we move to the third component, which is the viewing pipeline. Right. So, this viewing pipeline, what we are basically trying to achieve is through the interface which we have studied. Right. So, what do I mean by interface? The input specification, the way user would give you, and then you do the entire pipeline. Okay. So, the input specifications are very important. So, here what we are saying is that you have, so the word or the scene has to be described in word coordinate system, something like this. So, this is a coordinate system you have, and you have a scene description. Okay. And scene could be just the collection of polygons, right. That is what you can, let us say, handle at this time. Okay. And so, you can either build that scene yourself, or you can import it from somewhere. Import means there might be some scenes available to you as in some format, file format, where you have, let us say, the list of vertices and the polygons constructed using those lists. Polygon mesh. Okay, polyhedral object or polygon mesh. So, basically object is a collection of polygons, and that may be described through just a list of vertices and the corresponding polygons. Okay, so, such scenes may be available. So, you just can import them. Okay. Or just through the some interface or even through file input, you build the scene where you give the points, the end points of the polygons. Okay. So, here of course, you need some data structure to describe your polygon. Right. Okay. So, this specification of the scene, we call it in word. In fact, you can later on in the other assignment, we will also deal with this hierarchical modeling, where you have the models or the objects described in their own coordinate system, like a model coordinate system, and then you have the scene building using those coordinates. Okay, so, from modeling to the word or the scene coordinate system, and then use some sort of a scene graph to describe your scene. For the purpose of this assignment, have just a flat representation of objects, right. Okay. So, the scene is in word coordinate system, and then we also have the viewing coordinate system, right. So, viewing coordinate system is basically described by specifying the view reference point that is given in word coordinate, right. So, you have where the origin of the viewing coordinate system is located, that is what is the view reference point, right, which could be considered as the origin of the viewing coordinate system. And then you have these u, v and n directions for the viewing coordinate system, right. So, for instance, the direction v should be obtained from the up vector defined by the user. Okay. So, there is a notion of up vector which would be given by the user, and that is what you should use in order to obtain the v direction, for instance. Okay. And the extents of the window are basically defined in viewing coordinate system, right. So, the limits of the window size are in viewing coordinate system. The location of I with respect to the, let us say, the viewing plane should also be specified in viewing coordinate system, right. So, you understand what is defined in viewing coordinate system and what is defined in word coordinate system. Okay. So, through the proper transformations, right, word to view, that is what we have seen, we eventually get something like this, right. So, the viewing frustum gets built. You also need to specify the front or the near plane and the back or the far plane of this view frustum. Okay. Sometimes the view plane itself is considered as the near or the front plane. Okay. And so, there is a possibility for you to consider I lying along the n axis, right, that is where you will get such a configuration, or you may also have I off the n axis, right. So, for the purpose of this assignment, I have specified that you can have I along n axis, but again for experiment you can consider n I to be off the n axis. Okay.
Besides the transforms,
Right.
what else will change when you have it off the n axis?
Besides the transform, no, it won't change much, but the when it will change something when you need to render them. I am coming to that. Basically, see, I also require you to display the process what we are looking at. What I mean to say is that whenever you have each of these transformations happening, as a user from outside, I should be able to see what process has changed what, like a simulation. Okay, so, what I expect you to have is a simulation of this viewing pipeline, right. So, I will give you the example what I am trying to expect from you. Okay, so, there might be some changes with respect to when you make this I to be off n axis, right. So, again this is something like a bonus if you want to do it. Okay. So, obviously, once we have given this view frustum, we do the perspective transformation, right, which changes this to this, right. So, basically the center of projection which was lying here, now it goes to infinity. That is what the perspective transformation does, right, and you have this distortion here. Okay. And which also then requires you to put this into a normalized coordinate system, right, where you put everything between 0 and 1 for the depth. Okay. And this extents which were defined through the window are now mapping it to something like BL, VR, VB, VT, right. At times this is also considered like a viewport of your viewing pipeline. Okay. So, this transformation we have seen. Okay. So, why I am showing all these stages, because you have to demonstrate these stages, right. Okay. So, now let us say what is expected as output from this. So, what we have said is that the scene is defined in Word. So, I should be able to see the scene independent of your viewing pipeline, the pipeline which is intended to be implemented. I should be able to see the scene just using OpenGL, right. So, there is a combination of your viewing pipeline and what OpenGL does. So, it is a simultaneous learning. You write your own viewing pipeline and also learn about what OpenGL does for you. Okay, so, it is just a simple rendering of the scene using OpenGL. That is what the word is. Okay. That is the first thing. So, I should be able to see the scene. The second thing is the scene without clipping after transformation to the viewing coordinate system with its view frustum. So, I should be able to see that from an outside viewer. You see what I am saying? Okay. I will come to show this as an example. Yeah. So, I see the way the frustum is going to get built, I should be able to see it from some other viewpoint using OpenGL. So, that viewing pipeline becomes like a word for the OpenGL. That is what it is. Not clear, huh? Okay. Let me show the example. So, see, this is the scene in the word, right. The scene is defined in this word using this plane, these pillars, something there, these are boxes there, right. This is the scene which is defined in the word, and I am just seeing from one viewpoint using OpenGL. Fine. This is easy. All it requires you to do is learn about OpenGL viewing. Fine. Now, this is I want to see this also. Now, what have you done? You have basically applied all the viewing coordinate system changes, right. You have specified this I, okay, and this is the view frustum which gets built up using the transformations we have conducted. Right. So, here of course, the near plane and the viewing plane have been considered to be the same. This is my back plane, this is my front plane, and this is the scene with respect to this coordinate system. And again I am able to see this. You got it? Okay. So, now let us go back. So, what have we done? We basically have seen now the scene after transformation to the viewing coordinate system with the view frustum and where the camera is or where the eye is. All right. And then we would like to see the scene after perspective transformation and normalization. Okay. And then we see the scene after projection and clipping of the viewing plane. So, that is where you will bring in your clipping, because we are basically considering clipping in 2D. You could have done clipping in 3D as well, but that is going to be a bit hard. See, had there been only line clipping, then it would have been fairly easy. No, sides back. but you could try. I mean, nothing hurts. So, there of course, we are not asking for the filling part, because there you are talking only the wireframe rendering of the object, right. And of course, there has to be a facility by which you can change some of the input parameters. I should be able to change the location of I should be able to change the up vector, I should be able to change several other parameters which are specified by the user and see the result. Right. So, this is after this what we said, that you should be able to demonstrate the perspective transformation and the normalization. So, that has to be done in 2 stages, but the result which I am showing here is actually is a combination, because you basically take one parallel pipe to another parallel pipe, not a big difference, right. But this is what you would have once the perspective transformation and the normalization has been done, right. So, this is how the scene looks in this cuboid. So, you are able to see the cuboid as well as the scene within it, right. So, maybe to start with, you should consider your scene in such a way that everything comes within this cuboid, because if you take a large scene and then there is the view frustum which is built, in fact would cut it, right. So, normally there has to be a clipping, right. Is it clear what is being expected now? Okay. So, let me just complete the whole chain, right. So, this is what we have, and the last thing would be the image, right. That is the basically the image on the viewing plane, right. Here you would perform the necessary clipping and color them. Okay. So, what are we not considering here? We are discarding completely the hidden surface part. We are not incorporating it. So, you just take the list of polygons which get intercepted within it and just paint them or render them or color them using the filling, right. So, what it may not have is the right depth or the occlusion which you would otherwise have here, right. So, maybe to start with, you can consider a sparse kind of a scene where the overlaps are not there, therefore, you see it right. Right. Otherwise, what is going to happen is that if you happen to paint, let us say, the polygons with respect to this object later than this, you will see this and not this, although this is in front of this, right. So, this ordering is being discarded at this point of time, because we have not dealt with hidden surface elimination, right. So, at the end of this whole pipeline, what we have is this image. Okay. So, but you have to show the entire process. Okay. A little more complicated scenario I am showing it, which you do not have to do it, because at this point of stage you cannot. Pardon me?
So, we don't have to do the complicated scenario, but we have to do
this
type of scene.
Not this type of scene. I am not asking you to actually, I have just taken this as an illustrative example. I am not expecting you to make cones and these kind of stuff. Right now, I am asking you to just consider planar objects, just polygons. So, the scene complexity is of no criteria for this assignment, right. The functioning with respect to the various stages of the pipeline, these are important. not the complexity of the scene. Right. So, you can actually consider the kind of scene I showed in the beginning, just kind of a hut, or just take couple of boxes. Right. Okay, so, scene complexity is not something you should worry about at this stage. Right. But theoretically speaking, it does not matter if you can handle 10 polygons right, you can handle 100 polygons or 1000 polygons right. It shouldn't affect.
But then there will be hidden surface elements.
Yeah, that leaving apart, that leaving apart. Right. So, is this clear now? What is being expected?
The first part is fine till 20 seconds.
No, you have to do it. Okay, let me just give you the other example, which we actually have seen in the first class. So, here this is what we are expecting, right? This is what we want to do in a way. And this is the scene, and then this whole thing is now given within the view, right, within that scene. So, the camera is specified here, the viewing plane is specified here, and that is the part you see of this scene. And this is being done using the transparency and so on, right, which we have not dealt so far. But that is the idea. So, that you are able to demonstrate this whole pipeline, right, to anybody and simulate the process. Okay. So, this definitely requires you to also study about OpenGL, right? That is what is intended. So, you must understand what OpenGL does.
So 20 seconds is too early for all this.
Don't worry about the deadline, right? Because if you don't start, you will never do it.
We'll do it.
We start, sir.
We'll submit the first part at 20.
No. Because as I said, this is just the first assignment. There are two coming up.
So, for the other two, March and April will be fine. So 28th is fine enough.
See, we will worry about 20 seconds later on.
Yes,
Sir,
sir.
when?
Because we have minor also.
So let's talk about it when 20 seconds comes closer, right? Because if you don't start, I am sure you won't be able to do it. And you can't do this in one day. That much also I can tell you. So you got to start it right there. Okay. So is everything clear about the assignment? Because it's important, I thought, to give this kind of a role of the whole stages, right? Otherwise, things may not be clear when you read it. And the submission is going to be through the submission script, right, which I will post it. So, and I expect that you all actually use the Linux cluster. OpenGL is installed there, so there should not be any problem. Fine. Okay, thank you.